So we have covered symmetric tensors in the last class, and we have seen that symmetric tensors can be given a spectral decomposition, right? We have seen that S is equal to summation lambda I, Ei star, diagonal Ei star. So this is when you write S referred to the principal basis, then you can write it in this particular way. So what we will see today is that this spectral decomposition plays a very key role in proving properties of other kinds of tensors. So today we are going to look at positive definite tensors and also the polar decomposition of a tensor. So this polar decomposition will play a very key role in material frame indifference and other things also. So let us start with positive definite symmetric tensors. Positive definite tensors. So we will denote this by P-sim. So P stands for positive definite and sim of course for symmetric tensors. So we'll denote this set of positive definite tensors by P-sim. So let us define what we mean by P-sim. So S belonging to sim is said to be positive definite. It will be positive definite if u comma su is greater than or equal to 0 for all u belonging to V with u comma su is equal to 0 if and only if u is equal to 0. So this is the definition. So this is the inner product. So the inner product between u and su, if that is greater than or equal to 0 for all u, then this tensor is said to be positive definite, and if you have u comma su is equal to 0, if and only if u is equal to 0. So this part is also very important. Suppose if you drop this particular condition here, right, that it is just greater than or equal to 0 for all u, but we don't insist on this particular condition, then it is said to be positive semi-definite. Okay, so instead of positive definite, you will get positive semi-definite if you just have this particular condition but not this condition. So that means you can have u comma su is equal to 0 even if u is non-zero. Then in that particular case, we will say that it is positive semi-definite instead of positive definite. Yes, so let us see why. So if you take any book on linear algebra or matrix algebra, you will see that they always talk about symmetric positive definite tensors. So always the word positive definite is always accompanied by symmetric in the beginning. Okay, so why is it that people don't talk about arbitrary positive definite tensors? Okay, so we'll see the reason for that. So if I write now T, so let us take the positive definiteness of an arbitrary tensor T. So suppose if I write T is equal to Ts plus T skew symmetric. So we have seen that any tensor T can be decomposed uniquely into a symmetric part and an anti-symmetric part. So if I write now that u comma Tu, this I can write as u comma Ts of u plus u comma T skew symmetric times u. And then now you can see that this u comma Ts of u is 0, correct? So that is because T skew symmetric is this property that a skew symmetric tensor, when you take an inner product with u, then that is equal to 0. So this we have already seen, right? So the proof was that if you recall, the proof was u comma wu is w transpose. We use the definition of the transpose. Here w transpose is minus w, so minus of wu comma u, and then because u comma w is minus u comma w, so u comma w is 0. So this part is 0. So basically you can see that the positive definiteness of a tensor is decided totally by the symmetric part of that particular tensor here. And so that is the reason that whenever you look at any book on linear algebra or matrix algebra, they will only talk about symmetric positive definite. So they don't talk about arbitrary positive definite tensors because of this property, that in any case only the symmetric part of the tensor will decide whether it is positive definite or not. Fine. So now, so from now on we will also restrict ourselves to symmetric positive definite tensors and not to arbitrary positive definite tensors here. Fine. So now let us look at characterization of positive definite tensors. So theorem. Now let S belong to sim, then TFAE again. So this TFAE, as you already know, the following are equivalent. One is that S belongs to P sim. Two is that lambda I greater than 0, I equal to 1, 2, 3. So in this case, because we are dealing only with 3-dimensional space, so the number of eigenvalues is only 3. But if you are in an n-dimensional space, then actually this would range from 1, 2, 3 up to n. And the third property is that I of S is greater than 0. So this I is the set, so I of S is the set I1, I2, I3. Okay, so it's the set of all the principal invariants of a second order tensor here. So these are the three things that are equivalent. So if S belongs to P sim, then all the eigenvalues are positive. If all the eigenvalues are positive, then S belongs to P sim. Similarly, if all the eigenvalues are positive, all the principal invariants are positive. If all the principal invariants are positive, all the eigenvalues are positive. So they are equivalent. Okay. So let us try to show this particular equivalence here. Okay. So first, let us try to show the equivalence between 1 and 2. Okay. So if so 1 and 2, so 1 implies 2. Let us try to show that. So if S belongs to P sim, then the lambda i's are greater than 0. So if I write the eigenvalue problem, Sn is equal to lambda n, then if I take the dot product with n itself, so that is lambda n comma n, which is equal to lambda. Right? So this lambda is n comma Sn, and then by the definition, so n is some non-zero vector, and then since S is now assumed to be positive definite, then by the definition itself you will get that lambda is greater than 0. Since n is not equal to 0, you will get that lambda is greater than 0. Right? So this is true for all the eigenvalues, hence all the eigenvalues are positive when you have positive definite symmetric tensor. Right, then now let us try to show that if lambda I are greater than 0, then S belongs to P sim. So for that, this spectral decomposition is very, very critical. So let us try to prove this particular property here. One. Okay, so let me just write that again. So S is equal to summation lambda I, EI star dialectic EI star, and S times U is summation lambda I, UI star EI star. Okay, so that is just UI star. UI star is nothing but U dot EI star. And then from this, if I take the inner product with U, so U comma SU is equal to summation lambda I UI star the whole square. Okay, because again you will get U comma EI star, which is again UI star, so I will get lambda UI star the whole square here. And this is I ranging from 1 to 3. So if now lambda I, each lambda I is greater than 0, and then UI star square is obviously greater than 0, so it's a sum of positive quantities, hence U comma SU will be greater than 0. Right? So this is greater than 0 since lambda I greater than 0 for I equal to 1, 2 and 3. Right? So So what we have shown is that if S belongs to P-sim, then all the eigenvalues are positive. If all the eigenvalues are positive, then S belongs to P-sim. So that is what we have shown. Now we will show that 2 implies 3 and 3 implies 2. Okay, so let us try to show that. So one of these implications is fairly easy, but the other one is not so easy here. So if so let me write the expressions for, so this is lambda 1 plus lambda 3, I2 is equal to lambda 1, lambda 2, plus lambda 2, lambda 3, plus lambda 1, lambda 3, and then I3 is equal to lambda 1, lambda 2, lambda 3. Right? So now, if all the lambdas are greater than 0, right? So if lambda I greater than 0, then this implies that I of S greater than 0, because you can see from this that I1 is greater than 0, I2 is greater than 0, and I3 is also greater than 0. So this part of the proof is fairly trivial, but now to show that if I1, I2, I3 are greater than 0, then lambda i's are greater than 0 is not so trivial. So let us try to show that. So if I write the characteristic equation, so converse now, so converse implication, conversely, if I of S is greater than 0, then so let us now take, we want to show that lambda i's are positive, right? So so if I write now, each eigenvalue has to satisfy the characteristic equation, lambda I square plus I2 lambda I minus I3 is equal to 0, right? This is for I equal to 1, 2 and 3. So each eigenvalue has to satisfy this characteristic equation. Now, since all the principal invariants are positive, your I3 is also greater than 0, and so you have that lambda 1, lambda 2, lambda 3 is greater than 0, correct? So we now know that basically it cannot be 0, because if any of the eigenvalues is 0, then this will get violated, right? So so from this, this implies that lambda I is not equal to 0, correct? So that it shows that, right? Now, what is the other possibility? That the lambda I is negative, let us say. Okay, so now if lambda I is negative, so then let us write that. So if lambda I is less than 0, then let us call this as star. So star will get violated, because see then you'll get this is negative, this is negative, this is negative, this is negative, right? So it's a sum of negative numbers, and that cannot be equal to 0. So if lambda I is less than 0, then star gets violated, right? Star gets violated. So so hence lambda I greater than 0, hence lambda I greater than 0. So you can see this is a very, very elegant proof, and in fact actually this proof was suggested by one of the students who was attending the class. So that was very, very nice. I mean, one can always give a brute force proof, but brute force in the sense that I can try to write the roots of lambda I in terms of I1, I2, I3 and then try to prove it. That would be extremely cumbersome. The nice thing about this proof is that it can even be extended to n dimensions also, right? Very, very easily. The same proof, almost the same proof goes through, even if it's even if your underlying vector space is n dimensional. So it's a very, very elegant proof. So that completes the proof of this particular theorem here. Yes. Now let us look at the square root of a positive definite symmetric tensor. See, whenever we talk about positive numbers, right, we can define square roots of a positive number. So for example, square root of 9 is 3, right? Square root of 16 is 4. So whenever we are talking of positive numbers, we can define a square root, right? Without getting into complex valued numbers and so on. So positive definite tensors are also like positive numbers in the sense that they have a square root, and that square root, if you restrict the square roots to the class of positive definite symmetric tensors, then there is a unique square root in that set. So let us try to show that such a square root exists for positive definite tensors, and that it is unique if it is restricted to positive definite symmetric tensors. So theorem now. If S belongs to Psim, now if S belongs to Psim, there exists a unique H belonging to Psim such that H square is equal to which is H times H, which is equal to S, and H is called as the positive definite square root of S, and we will write H as square root of S. So we have to be very careful how we interpret this square root of S. So it doesn't mean, so whenever I write this square root of S, it doesn't mean that I am taking the square roots of individual components. Okay, so the root of S 3, so like this. So this is not what I mean, right? So the square root is to be interpreted in this particular sense here, that if you take this tensor H and if you multiply it with itself, then you will get back the original tensor S. So the square root is to be interpreted in this particular way and not as the square root of the individual components of S. Okay. Yes. So let's see. So this. So first thing, so just a few clarifications before we start on the proof of this particular theorem. So actually, if you look at the square roots, so you can have multiple square roots. Okay, so for example, if you take identity tensor, then diagonal of 1, 1, 1, okay, would be a square root, because if you multiply this by itself, you will get the identity. So diagonal means a diagonal tensor. Okay, so this, if I take diagonal of 1, minus 1, minus 1, and if I take the square of this, then again I get I. Okay, so actually there are multiple square roots even for a positive definite tensor. So I is a positive definite symmetric tensor. There are multiple square roots. But then what does this uniqueness mean? So what this uniqueness means is that if we restrict the set of square roots to the set of positive definite symmetric tensors, then there is a unique element. So let me just draw this picture here. So there are lots and lots of square roots. So this is Psim, right? Then actually there are lots and lots of square roots for any given tensor. But if you take the square roots in Psim, there is only one. Square root in Psim. Okay, so this uniqueness is to be interpreted in this particular way. That although there are many square roots, there is only one square root which lies in Psim. So the uniqueness doesn't mean that there is only one square root. Uniqueness means that there is only one square root in Psim. So that is the correct way of interpreting this particular theorem. Okay, so now let us try to prove this particular theorem. So so again, as I have already indicated, the spectral decomposition plays a very critical role in all the proofs that we are going to do. So this, so we have that S is equal to summation lambda I ei star dividing ei star, right? And these lambda i's are positive, right? So because this we have already shown in the previous theorem that a positive definite tensor has positive eigenvalue. So each of these lambda i's is strictly greater than 0, correct? And so, so here just I will mention that if it is positive semi-definite, then in that case the lambda I are non-negative. Okay, so non-negative means that they can be 0 also, or they can be positive, but they cannot be negative. So that's but right now, I mean, we'll restrict ourselves to positive definite, but I'm just indicating what positive semi-definite also means. So then in that case, the eigenvalues have to be non-negative. But here in this case, the eigenvalues are strictly positive. So we can define now. So define h to be equal to summation of square root of lambda I star divided ei star. Okay, so this is I equal to 1, 2, 3. Now you see that if you take the square of this, then you will get back s, right? So so first of all, h is symmetric because you are using the ei star divided ei star, which is a symmetric tensor, and so that is the reason that h is symmetric. So so this implies that h square is equal to s. Okay, so clearly this is a square root of s in this sense, that h square is equal to s, and it is also positive definite because if lambda i's are positive, then the square root of lambda I is also positive, right? And so hence the eigenvalues are also positive, and so this h belongs to Psim, right? So h belongs to Psim because the eigenvalues are positive and it is also symmetric. Now we have to show that h is unique, right? Such a square root in the space Psim is unique. So let us try to show uniqueness now. So first, see, always remember that in any proof of uniqueness, first you have to show that it exists. See, if there is no existence, then there is no question of uniqueness. So always before addressing uniqueness, one has to show that such a tensor exists. So we have shown that at least one positive definite symmetric tensor, square root of this tensor exists. Now we want to show that that it is unique. So if I write now, let me write the eigenvalue problem for s. So I will write it as s minus lambda I times n. And this I will write as equal to h square minus lambda I times n, which is equal to h plus square root of lambda I times h minus square root of lambda I times n. So I'm writing this for one particular eigenvalue. So it could be any of the three eigenvalues, it doesn't matter. So I'm just writing the eigenvalue problem in this particular way. Okay, so we can write it in this particular way. H plus root lambda I times h minus root lambda I times n is equal to 0. Okay, fine. Now we will call this vector as n bar, this particular vector here. Let me call this as n bar. Okay, so let n bar be equal to h minus root lambda I times n. So now this particular statement I can write. So now this implies that 0 is equal to h plus root lambda times I times n bar is equal to 0. Okay, and this will imply, oh sorry, no need of this 0, already have put a 0 here. So this implies that n bar is equal to 0. Okay, otherwise, see, suppose if n bar is not equal to 0, then minus of root lambda would become an eigenvalue, right? So otherwise, so suppose if it is a non-trivial solution, then it becomes exactly like an eigenvalue problem with minus of root lambda as an eigenvalue of h, but that would violate the positive definiteness of h. But we are given that h is a positive definite symmetric tensor. So otherwise, minus of root lambda would be an eigenvalue, right? So this violates the positive definiteness, right? Violating positive definiteness of h. Okay, so it cannot be the case, and hence you have n bar is equal to 0. And then now what is n bar? So n bar, so this implies now that h minus root lambda I times n is equal to 0. Right? And then now we see that h has to have root lambda as the eigenvalue and n as the eigenvector. Right? So this implies that root lambda and n have to be eigenvectors of h. Have to be eigenvector of h. So if lambda n are the eigenvalues of S, then root lambda n have to be eigenvector of h. Okay, so that's what we have shown. And hence then from the spectral uniqueness of the spectral decomposition, so from the uniqueness of spectral decomposition, from the uniqueness of the spectral decomposition, h has to be equal to root of summation I equal to 1 to 3 of root lambda I ei star dyadic ei star. So it has to be of this particular form. So and the spectral decomposition is also unique, so it has to have this particular spectral decomposition. So that's what we have now shown. Okay, so to summarize, we have shown that given a positive definite symmetric tensor, there exists a unique square root tensor in the positive definite, in the set of positive definite symmetric tensors. So we'll use this result now to prove the polar decomposition theorem. So polar decomposition. So let F be an invertible tensor. Let F be an invertible tensor. So invertible means det F is not equal to 0, right? Or det F not. It can be positive or it can be negative, but not equal to 0. So then it can be factored. Then it can be factored in a unique fashion as f is equal to Ru is equal to Vr, where R belongs to orth and UV belong to Pism. So this U and V are symmetric positive definite tensors, and R is an orthogonal tensor. Not necessarily a proper orthogonal tensor. So actually that will depend on the sign of det F. But so that we will see at a later stage. But right now, let us just try to prove this particular theorem here. So proof. Okay, just one second. I think I forgot to mention one thing here. So this, I forgot to mention this, that U is actually under root of F transpose F, and V is equal to square root of F transpose. Okay, so we have explicit forms for U and V as well. So we need to show that also. So first, for the proof, this F transpose F is obviously symmetric, right? It belongs to sim. Okay? Because if you take the transpose of this particular tensor, you get back the same object. So F transpose F is obviously symmetric. It is also positive definite. Okay, so that is not so obvious. Let us try to see that. F transpose F times U. This you can write as Fu comma fu. Right? Now this fu is just some vector, right? And by the definition of an inner product, this v comma v, right? V comma v is always greater than or equal to 0. Right? So this f of u comma f of u is always greater than or equal to 0. And we need to show that there is equality in this inequality if and only if u is equal to 0. So here, if u is equal to 0, then obviously fu comma fu is equal to 0. Conversely, if fu comma fu is equal to 0, so conversely, so if fu comma fu is equal to 0, then fu is equal to 0, right? Because this is just following from your inner product, the definition of the inner product, right? So then from that you will get that u is equal to 0 because f is invertible, right? So you can always multiply this by f inverse, right? So f inverse exists, so that's why f inverse multiply by f inverse. So just say multiply by f inverse, right? So then you will get that u is equal to 0. So what we have shown is that f transpose f does belong to P sim, right? So this whole thing implies that f transpose f belongs to P sim. Then we can talk about square roots, right? Because in the previous theorem we have shown that every positive definite symmetric tensor can be, you can find a square root of any symmetric positive definite tensor. So let u be equal to square root of f transpose f, right? And so now we know that this itself also belongs to P sim, right? So we are considering the unique symmetric positive definite tensor which lies in P sim, right? So this is from the previous theorem, and now if you define R as f times u inverse, then we will show that this R is an orthogonal tensor. So let us try to show that. So first we will define, define R as equal to f times u inverse, right? And so from this obviously you get that f is equal to Ru, right? So this we already know, but now we want to show that R is orthogonal. So how does one prove that? So R transpose R is equal to, so take the transpose of this. So this is u inverse transpose, which is going to be u inverse itself because u is symmetric. So I will get that u inverse. So let me first write it like that. Then f transpose, then f times u inverse, right? And so u inverse transpose is u inverse itself, and this f transpose f is nothing but u square, right? Because u is f transpose f. So this is u times u inverse. So this is equal to the identity tensor. Right? So you can see that R transpose R is identity here. Right. So yes, now actually let us look at the determinant of this. So determinant of f is equal to determinant of R times determinant of u, right? So now determinant of u is always going to be positive because u is a symmetric positive definite tensor, right? And so all its eigenvalues are positive, and the determinant is simply the product of all the eigenvalues which are all positive. So hence the determinant of u is always greater than 0, right? So determinant of u is greater than 0. So det f and det r have the same sign. Det f and that R have the same sign. Right? Have the same sign. So if that f is greater than 0, then R belongs to R plus, right? Because then in that case your determinant R has to be equal to plus 1 in that particular case, because if that f is greater than 0, then that R will be positive, and plus 1 and minus 1 are the only two possibilities for an orthogonal tensor. So it has to be plus 1 in that particular case, and so it will belong to R plus. So typically actually this f will be the deformation gradient, right? Typically, I mean later on when we actually apply this polar decomposition theorem to actual quantities in continuum mechanics, typically this f will be the deformation gradient. And we have seen that, or we have not seen it at this stage, but we will see later that f is greater than 0. Okay, so that's known as the orientation preserving condition. So that we will see at a later stage. So since that f is greater than 0, this R will always belong to orth plus. Yes. So that completes one part of the proof. Now we want to show that it is also equal to VR. So define now. So let V V be equal to f times U times R inverse. F inverse. So that is equal to f times R inverse, which is equal to RU times R inverse, which is equal to R times U times R transpose. So I just define V to be, so this is definition, colon equal to f U f inverse, and then we have seen that U times f inverse is R inverse because f is equal to RU, and then so from that I will get that R inverse is, so f is RU, and so I substitute RU, R inverse, and R inverse is R transpose, so I get RU, R transpose. And we know that if you pre and post multiply any tensor by an orthogonal tensor, then all the eigenvalues and the principal invariants, they all remain the same, correct? So then because of that, V will also have the same eigenvalues as U. And since all the eigenvalues of U are positive, all the eigenvalues of V are also positive, and it is also clearly symmetric. So V belongs to sim, right? And all the eigenvalues. So let me write it as lambda I of V are the same as lambda I of U, because they are orthogonally equivalent. They have the same characteristic equation, and so since all the eigenvalues of U are positive, all the eigenvalues of V are also positive, and hence it's a positive definite symmetric tensor here. So this implies now that V belongs to P sim. Right? So this implies that V belongs to P sim. Yes, and if you take now F times F transpose, so let us just write that here somewhere. So F times F transpose now is equal to VR times R transpose times times V transpose, and R transpose is equal to identity, so this will become V square, and so V will be equal to square root of F transpose. Okay, so that also we have now shown. So basically U is under root of F transpose F, and V is under root of F transpose F. So these are the things. And so what about uniqueness? So we have already shown that U is unique, right? Because it's a square root. And V is also unique since it is the square root of that. And what about R? So R is just F U inverse, right? R is equal to F times U inverse. So that also is unique. Because F is unique, F is given, so there is no question of uniqueness for F, but U is unique, and so F times U inverse is unique. Right? So, unique. So if, to summarize, if determinant of F is not equal to 0, then the polar decomposition is unique, right? So that means R is unique, U is unique, V is unique, but now what happens if F is determinant of F is equal to 0? What happens in that case, right? If determinant of F is equal to 0, right? If determinant of F is equal to 0, then actually you can show. So go through the same proof again, right? You will see that U and V are still unique, right? Are still unique. But R is not unique. See, the way we defined R was as f times u inverse. But now u will not be invertible when det f is equal to 0, because the product of the eigenvalues is 0, right? So still unique, but not positive definite, right? But not positive definite. Or you can say, but they are positive semi-definite. They are positive semi-definite. So that means the eigenvalues are non-negative, right? So some of the eigenvalues can be 0 in this particular case, and hence they are not invertible. And so you cannot define R as f times u inverse. So R is not unique in this case. R is not unique. So if det f is 0, so again we will not come, I mean in continuum mechanics we will not generally encounter this case, but just as a piece of information that if f is singular, then u and v are still unique. They are positive semi-definite instead of positive definite, and R is also not unique here. So this is the summary in case your f is singular. Yes. So we'll move on. So that sort of completes the analysis of symmetric tensors. Okay. We'll now move on to isotropic tensors now. Isotropic functions. So at this stage, we will simply define these things in a mathematical setup, and then later on we will apply them to isotropic materials. Okay, so that application we will see at a later stage. Right now, we will just talk about these things from a mathematical sense, what we mean by isotropic functions. Isotropic functions. Scalar function, phi from P sim to R is an isotropic function. Then isotropic function if it remains invariant under orthogonal transformations. If it remains invariant under orthogonal transformations. So that means phi of S is equal to phi of Q S Q transpose for all S belonging to P sim and Q belonging to all class. Okay, so this is for a scalar valued function, and similarly for an isotropic tensor valued function. So an isotropic tensor valued function. Function G, which maps from P sim to sim, is one that satisfies Q times G of S times Q transpose is equal to G of Q S Q transpose. Okay, so this is the definition for a tensor value. So this G is now a second order tensor of S here, and so we define an isotropic tensor valued function in this particular way. Okay? So P sim and Q belong to all class. So we will restrict ourselves to the set of proper orthogonal tensors, because in most applications Q will be a proper orthogonal tensor here. Okay, so here actually while defining these isotropic functions, one has to be a little bit careful that, see for example, phi is a function of S, right? But they are also writing phi of QSQ transpose. Now, this QSQ transpose, so we are mapping it from P sim to R. So we should be careful that this QSQ transpose also belongs to P sim. Okay? So actually again, fortunately that is the case, because if S is belonging to PSym, right, then QSQ transpose will also belong to PSym, because the eigenvalues of S and QSQ transpose will be the same. And so note here that QSQ transpose belongs to PSym, right? When S belongs to PSym. So that is very important, because see, otherwise, see, this phi has to be a mapping from PSym to R. So so this argument has to belong to PSym. Otherwise, this whatever we are writing here will get violated. So we have to be careful that whatever is the argument here is also belonging to PSym in this particular case here. Fine. So first thing that we will show is that the list of principal invariants is isotropic. Okay. So let us first show that. So yes. So the list of the theorem, the list of principal invariants, I is isotropic. So this I actually includes I1, I2, I3, all three of them. Okay, so that means what we want to show is that I of S is equal to I of QS Q transpose. So this phi in this particular case is just the principal invariants here. So we know that they are just scalar valued functions, and so we are trying to show that they are isotropic functions in this particular sense here. So let us try to prove this. Okay, so the proof for this. So I will show that actually the characteristic equation for S and for QSQ transpose is the same. So once the characteristic equation is the same, that means the coefficients of the lambda I, right? Lambda I cube minus I1 lambda square plus I2 lambda minus I3 is equal to 0, right? That is the characteristic equation. So if the characteristic equation is the same, that means the coefficients of the lambdas are lambda square, lambda, and so on are the same. So that means the principal invariants are the same, right? So we'll show that the characteristic equation is the same. So determinant of Q as Q transpose minus lambda I. If I can show that this is the same as determinant of S minus lambda I, then I am done, right? So this I write as determinant of Q as Q transpose minus lambda Q transpose, Q transpose, and this I can write as determinant of Q times S minus lambda I times Q transpose, which is equal to determinant of Q times determinant of Q transpose times determinant of S minus lambda I, and this I can combine. So this again I can write as determinant of Q transpose times determinant of S minus lambda I. Q transpose is identity, so determinant of Q transpose is just 1. So this is equal to determinant of S minus lambda I. So what we have shown is that the characteristic equation of Q as Q transpose is the same as S, and if the characteristic equation is the same, then that means the principal invariants are also same. So effectively what we have shown is that all the principal invariants are isotropic functions, right? So that is I is isotropic. The set of principal invariants are scalar valued isotropic functions. That is what we have now shown here. Fine. Okay, so then now for the next result, we will need one result from functional analysis. Okay, so let us look at that result. So let x, y, z be some vector spaces. vector spaces, and let f from x to z and g from x to y be two mappings, such that x prime belonging to x and g of x equal to gx prime implies that f of x is equal to f of x prime. Then there exists a mapping h from g of x, which is a subset of y, to z such that f of x is equal to h of g of x. Okay, so there exists this mapping h such that this f of x is equal to h of g of x. Now this may look a little bit complicated, so we will try to draw a figure to show what exactly is this theorem here. So let us draw this thing. So this f, so this is your x and this is your z and this is your y, let us say. Okay, so these are the three sets here, and f is a mapping from x to z, so this is a mapping, f is this particular mapping here, and g is from x to y, so this is your g, which is from x to y now. Okay, and then we say that if x and x prime are two different points here, so if we take two different elements of x, okay, and if g of x equal to g of x prime implies, so this g, so suppose now g of x prime, suppose if g of x equal to g of x prime implies that f of x equal to f of x prime. So now this is your mapping here. So let us write this. So suppose if there are two distinct elements x and x prime in x, and if g of x equal to g of x prime implies that f of x equal to f of x prime, then there exists a mapping from y to z. So that means there exists now, so suppose this is a subset of g of x, so there is a mapping from this set to this one, that is called that h. So this is h of g of x, right? So your f of x is equal to h of, so g of x will map it from here to here, then h of g of x will map it from here to here, right? So your f will be equal to h of g of x. Okay, so that is that last line, that is this one here. Okay, so let us try to, so this theorem is an existence theorem, so which can be found maybe in books on functional analysis. So we are not going to prove this particular theorem, but we will apply this particular theorem to prove, to show that to prove the representation theorem for isotropic scalar valued functions here. So right, so I'll just keep this statement here because we will use this particular statement of the theorem here. So theorem, representation theorem. So representation theorem. For isotropic scalar functions. Isotropic scalar functions. Okay. So let us try to show this. So function phi now. Function phi from p sim to r is isotropic. Is isotropic if and only there exists a function phi tilde from invariants of S to R such that phi of S is equal to phi tilde of invariance of S. Okay. So what basically this theorem says is that any scalar valued isotropic function has to be a function of the principal invariance of S. That is what basically this theorem is saying here, right? So let us try to show this particular theorem. So proof. So actually in one direction the proof is fairly trivial. So if you are given that, so because it's an if and only if theorem, right? So you have to show it in both directions. So if, so let me call this star. So if star holds, right? If star holds, then phi of Q as Q transpose is equal to phi tilde of I of Q as Q transpose, and we have shown in the previous theorem that the invariants of Q as Q transpose are the same as the principal invariants of S. So this is I of S, which is equal to phi of S. Right? Phi tilde of I of S is phi of S. So we have shown that if star holds, then phi is an isotropic function, right? So the converse is a little bit harder. So conversely, we want to show that if phi is a scalar valued isotropic function, then it must have this particular form. That means there must exist a phi tilde, which is a function of the principal invariance of S. Yeah. So conversely, we need to show that if invariance of A equal to invariance of B implies phi of A is equal to phi of B. Okay, so let me make a connection. So basically we are going to use this particular theorem here, whatever I had written earlier. So let me make a connection between this. So your G, this function G is exactly like this invariance here. So I'll just try to make a connection with this theorem here. So the G is like this principal invariance, and if that implies f of x equal to f of x prime, so that is this phi. So this f is like your this phi function here. So this is G, your f is like phi, okay? And your h is like the phi tilde. The h is like the phi tilde, right? So I think you can make the connection that if you are invariant, so if A and B are two positive, symmetric positive definite tensors, if their invariants are the same, implies that phi of A is equal to phi of B, then by this theorem there exists an h, right, which is this phi tilde, let us call it, which is a function of g of x, right, which is, so the g of x would be the invariant, so it has to be a function of the principal invariant. So now I have made the connection with this function from, with this theorem from functional analysis. Now let us try to show this particular thing here. Right? So we want to show that I of A equal to I of B implies phi of A is equal to phi of B. So let us try to show this. So let us write A now as equal to summation of lambda I EI star divided EI star, let us say, right? Or let me just write it as EI. So the EI need not be the canonical basis, it is just the eigenvectors of A itself. And your B can be written as summation of lambda I times EI prime, let me call it EI prime times EI prime. So the because the principal invariants are the same, the eigenvalues have to be the same, right? Because the characteristic equation is going to be the same, and hence the eigenvalues are the same. So here you can see that A and B will have the same eigenvalues, but the prime means that the eigenvectors are different. Okay. Now I can connect the eigenvectors. See, because both are orthonormal sets of vectors, right? The EIs are also orthonormal, and the EI primes are also orthonormal. So I can connect them through orthogonal tensors here. So since EI and EI prime are orthonormal basis, there exists Q belonging to R plus such that this EI is equal to Q times EI prime in this particular case here. Right, so I mean, we have seen lots and lots of examples of this already, right? So if you recall, we had a relation like EI bar was Q transpose EI, things like that when we were doing the change of basis. So this is very similar. So if you have one set of orthonormal basis, you can transform it to another set of orthonormal basis if you multiply each of them by Q, right? So QE1 bar or even prime will take you to E1, QE2 prime will take you to E2, QE3 prime will take you to E3. So this we have already seen earlier. So you can easily construct this tensor Q such that Q times EI prime is equal to EI. Okay, then now let us write Q times B times Q transpose is equal to summation of lambda I times Q times EI prime dyadic EI prime times Q transpose. Right? You can write it in this particular way. And now we will use some of the properties. So if you recall some of the properties, so T times A dyadic B is equal to TAA dyadic B. Now use this property, and also A dyadic B T is equal to A dyadic T transpose B. Okay, so these are some of the properties of the dyadic products which we have shown either in the class or in your assignments. You may have shown them. So we will use those properties here, right? So, so this is T transpose times B. Yeah. So if I apply that to this particular line here, so this particular thing can be written as summation lambda I times Q times EI prime dyadic Q times EI prime. So this is how you can write it. And we have seen that this Q times EI prime is EI. So this is equal to summation lambda I EI dyadic EI, which is nothing but A itself, right? So which is equal to A. So finally, what we have shown is that Q times B times Q transpose is equal to A. Okay, so that is what we have shown. Okay, so let me just write that here. Yeah, so we need to show this. Right. So what we have shown is that okay. So what we have shown is that what we have shown is that Q times B times Q transpose is equal to A. That's what we have now shown. Okay, and since phi is isotropic now, since phi is isotropic, we will get that phi of A now is equal to phi of QB Q transpose, right? And because it is isotropic, so this is equal to B, right? So from here to here is assumed isotropy, right? Assumed isotropy of phi. So from that step to that step, we can go from this step to this step because of the assumed isotropy of phi. So that is what we wanted to show, that we started out with IA equal to IB, and now we have shown that phi A is equal to phi. And hence now we can invoke that function, the theorem from function analysis, to say that there exists now a phi tilde which has to be a function of the principal invariant. Okay, so to summarize this discussion, any isotropic function can always be expressed as a function of the principal invariants, right, of S basically. Okay, so that is the theorem that we have now proved. So this gives a characterization of scalar valued isotropic functions. Okay. So similarly, there is a characterization of tensor valued isotropic functions, which is known as the Rivlin-Eriksson theorem. Okay. So probably after Rivlin and Eriksson, who proved it for the first time. Okay. So let us try to prove this theorem. So actually the proof is very lengthy, but we will start on that theorem. So let me just first state the theorem, and at least the easy part of the proof I will prove it, and the difficult part of the proof I will keep for later. Okay. So theorem now. So this is the Rivlin-Eriksson theorem. Rivlin-Eriksson theorem. Representation theorem. Representation theorem. Right. So a function g from p sim to sim is isotropic. If and if there exist scalar functions phi0, phi1, phi2 from invariants of S to R such that G of S is equal to phi naught invariance of S times I plus phi1 invariance of S times S plus phi2 invariance of S times S squared. So this is the for all S belonging to P sim. Okay, so for all S belonging to P sim. So note that actually, although S belongs to P sim, G of S belongs to sim, not to P sim. Okay, so I mean, so this is a mapping from P sim to sim. Okay, so this entire tensor belongs to sim, not necessarily to P sim. Okay, so let us try to prove the easy part of the proof here. So again, you can see that this is an if and only if statement. So again, let me call this as double star or whatever. So if double star holds, then let us first try to show that this g of s is an isotropic function. And as I said, that the difficult part of the proof, that is a converse, that we will show in the next class. So here, so proof. Okay, so proof. So g of, so if double star holds, let's say, if double star holds, then g of q as q transpose is equal to phi naught of I of q as q transpose times I plus phi1 of I of q as q transpose times q as q transpose plus phi2 of I of q as q transpose times q as q transpose times q as q transpose. Right? So just wherever S occurs, put q as q transpose, right? Because we want g of q as q transpose. So yeah, wherever S is occurring, I am just putting it as q as q transpose. Now we have seen that the principal invariants of q as q transpose and S are the same. So I can write this as phi naught of I of S. I will write this I as q transpose plus phi1 of I of S times q as q transpose. And see here, now q as q transpose multiplying q as q transpose. So this q transpose q will give identity. Then this, so what will happen is that this whole product will go to q times s square times q transpose. Okay, so let me just write it in that way. So this is plus phi2 of I of S times q times s square times q transpose. And this I can write as q times g of S times q transpose. Right? Because so g, if you write it as phi naught of I plus phi1 times S plus phi2 times S square, you will see that q times g of S times q transpose is this particular line here. So what we have shown is that if double star holds, then g of s is a tensor valued isotropic function, right? So, so this implies that g of s is a tensor valued isotropic function, right? Isotropic function. Okay, so the converse is of course much more difficult. So what we want to show is that if g is a tensor valued isotropic function, then it has to have this particular form, right, which is in this double star here, and that is much more difficult to prove. So that I think we will prove in the next class. But just to point out what is the difficulty in proving the converse here, right? So the difficulty is that, see, suppose if I knew that g of s is always a polynomial function of s. Suppose if I knew that, right? Suppose somebody proved that g of s always has to be some polynomial function of s, then actually the proof would be quite simple, because then I can just assume some polynomial, and then by the Cayley-Hamilton theorem, the polynomial can always be reduced to ISS square, and then it would be just a matter of proving that these phi naught, phi 1 and phi 2 are functions of the principal invariant. But the problem with this proof is that we do not know that it has to be a polynomial function, right? So we cannot assume that it is a polynomial function, and hence the proof is very difficult. Okay, so that we will see in the next class.